Welcome back for part 2 of L'Hopital's rule. So here I'm handed a limit. My job is to evaluate the limit. First thing I always do is direct substitution. So by direct substitution, I've got 1 squared plus 2 over 2 times 1 plus 1, 2/3, and I'm done. No L'Hopital's rule needed. Now you might be wondering, why did he put this one in here? Because I have found in the past that because we are in the section on L'Hopital's rule that everyone just simply assumes, always use L'Hopital's rule. So then they get this. And they get the wrong answer because math told them that. Okay. Remember, we only use L'Hopital's rule for 0 over 0 or plus or minus infinity over plus or minus infinity. Okay? You can apply L'Hopital's rule incorrectly to a lot of things, and you can get wrong answers all day long. So be careful. Always check. Okay? Does L'Hopital's rule work for one-sided limits? Most definitely it does, but let's make sure we need it first. Direct substitution. I'm going to get the sine of pi divided by 1 minus cosine pi. The sine of pi is 0. Cosine of pi is, what is cosine of pi? Cosine of pi is -1, so I have 1 minus a -1. 1 minus a -1 gives me 0 divided by 2. What's 0 divided by 2? Well, 0 divided by 2 is 0. Don't need the L'Hopital's rule. So what I'm saying here is check. Check to see if you need L'Hopital's rule before you just start applying it. Final exam's coming up, and there'll be a couple of limit problems on the final exam. Some might need L'Hopital's rule, some might not. So only use it if you need it. All right. L'Hopital's rule can actually be used for other forms. It can be used to evaluate limits of the form 0 times infinity, 1 to the infinity, infinity to the 0, 0 to the 0, and infinity minus infinity, if we can find a way to rewrite them algebraically so that they work out to be 0 divided by 0, infinity divided by infinity. So what I'm saying is, sometimes you're going to run across a limit where when direct substitution is applied, you're going to get 0 times infinity. And I don't know what nothing times everything is. But if I can find a way to algebraically manipulate that expression and rewrite it as one of the two acceptable L'Hopital's forms, I'm going to do that. Same thing here, 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 and here. If there's a way to rewrite to turn it into, then we can. If not, we have to find some other technique. So for example, here, if I attempt to apply direct substitution to this, so by direct substitution, I get e to the negative infinity times the square root of infinity. Now this is not math because you don't apply infinity, you don't plug in infinity. It's conceptual. We're talking about what's going to happen to e to the negative infinity. Well, e to the negative infinity really means 1 over e to the infinity, or as x gets larger and larger and larger, that gets smaller and smaller and smaller. And so we end up with a situation where we have infinity times 0, or in this case, 0 times infinity. Now, I can't do L'Hopital's rule yet because L'Hopital's rule only works if it's 0 divided by 0 or infinity divided by infinity. So what I'm going to do is I'm going to algebraically manipulate this expression to make it fit L'Hopital's definition. So, keeping the limit the same because I'm not changing the limit, I'm going to rewrite this as the square root of x over e to the x. Because what does e to the negative x really mean? Well, it really means put that e downstairs. And now if I apply direct substitution, I've got the square root of infinity, or infinity upstairs, and e to the infinity, or infinity downstairs. And so now I have a form, an acceptable form for L'Hopital's rule, and I can apply L'Hopital's rule to this problem. So now by L'Hopital's rule, I'm going to get the limit as x approaches infinity of 1 over 2 root x divided by e to the x, which then if I clean that up algebraically, I get the limit as x approaches infinity of 1 over 2 root x times e to the x. And now by direct substitution, I don't want that one. I've got 1 over 2 times infinity, or 0. And so if the yellow, or the gold if you prefer, is equal to infinity, that means that the blue is equal to 0. And if the blue is equal to 0, that means the original pink up there that I highlighted was equal to 0. Or in this case, 0 times infinity is equal to 0. Now, how does 0 times infinity equal 0? Well, approaching 0 must happen faster than approaching infinity happens. And because it gets there faster, the product of those two works out to be nothing, to be 0. All right, so let's talk about how we did this again. Given a limit, direct substitution tells me it's 0 times infinity. 0 times infinity is good, but it's not good enough. It's not good enough for L'Hopital's rule. Algebraically rewrote our limit argument so that it gave me infinity divided by infinity. And how did I do that? Well, I recognized that negative exponent just means put it downstairs. And so it gave me my infinity divided by infinity. Apply L'Hopital's rule, algebraically clean it up, evaluate it out, and I get 0. Numerator is fixed at 1, denominator gets larger and larger and larger and larger, and because that denominator keeps getting larger and larger and larger and larger, that value of that fraction gets smaller and smaller and smaller and smaller, approaching 0. Let's try it again. We're taking the limit as x approaches 0 from the right of x times the natural log of x. Right? If I do direct substitution, I'm going to get 0 for the x and negative infinity for the natural log of x. Okay? Remember, natural log graph looks like this. Right? And so as x approaches 0 from the right, meaning moving it on the graph in this direction, we're going down and down and down and down and down. So we're approaching, that is the natural log of x is approaching negative infinity. This is good, but it's not good enough. I need to find a way to rewrite this. Now, here's where things get tricky. In the last problem, it was kind of obvious how to rewrite it, because the negative exponent just said, hey, put me downstairs and life will be good. Here, we have to make a decision. So, if you have 0 times infinity, any infinity, positive or negative, and if we call this the f, and if we call this the function g, if you rewrite this as f over 1 over g, that's going to give you 0 divided by 1 divided by infinity, which is going to give us 0 over 0, which is good for L'Hopital's rule. But you could also rewrite as g over 1 over f, which would give us plus or minus infinity over 1 divided by 0, which is going to be some sort of infinity, which is also good for L'Hopital's rule. So we need to make a decision as to, do I rewrite this as f over 1 over g, or do I rewrite this as g over 1 over f? Here's the downside. Sometimes you might choose this one and then try L'Hopital's rule and it doesn't work, because it takes us down some rabbit hole where derivatives just need to keep getting reapplied and reapplied. It doesn't take us anywhere, which means that you might have to start over and try it the other way. Now, unfortunately, I cannot give you any insight as to which way to rewrite, because sometimes it works better f over 1 over g, and sometimes it works better g over 1 over f. There is no rule that says do it this way and it will always work. So I'm going to look at my problem and I'm going to say this. I don't want to deal with 1 over the natural log. So I am not going to do f over 1 over g. I'm going to choose to do g over 1 over f. Because this looks ugly. I don't want to do 1 over natural log and then have to take a derivative in a step or two when I do the L'Hopital's rule. So I'm going to rewrite my original problem as the limit as x approaches 0 from the right. I'm going to leave natural log up top, and I'm going to put 1 over x down bottom. Now when I do direct substitution, I have negative infinity upstairs, and I have positive infinity downstairs. 1 divided by a really, really small positive number is a really, really large positive number. So this is good. I can now apply L'Hopital's rule. I still have the limit as x approaches 0 from the right. Upstairs, the derivative of the natural log of x is 1 over x. Downstairs, the 1 over x is negative 1 over x squared. Right? With a little bit of algebra, I'm not applying L'Hopital's rule again, so I'm not writing down LH. But with a little bit of algebra, dividing by a fraction is flip and multiply, so this is going to turn into 1 over x times x squared over negative 1. Right? So I've got the limit as x approaches 0 from the right of negative x. So what is that going to give me? It's going to give me a big fat 0. And so the value of that limit is 0, which means the value of the green limit is 0, which means the value of the original problem is 0. Hey, we've seen 2 problems in a row right now where 0 times infinity works out to be 0. Should we assume from that 0 times infinity is always 0? And that would be a bad assumption because that is not always true. It just so happened it worked out twice that way, but it won't always work out that way. All right, what about this problem? I'm supposed to take the limit as x approaches infinity of 1 plus 1 over x raised to the x. Now, if I attempt to apply direct substitution, I get, well, what do I get? I get 1 plus 0 to the infinity, or 1 raised to the infinity. Well, what the heck does approaching 1 raised to the approaching infinity mean? I don't know. So is this one of the ones that I should be able to rewrite? Yeah, it's right there. It's 1 to the infinity. I should be able to find a way to algebraically manipulate this original expression here and somehow rewrite this as 0 times 0 or 0 divided by 0 or infinity divided by infinity. All right, so let's get this done. You ready for some algebra? If we say that y, some value y is equal to the limit as x approaches infinity of 1 plus 1 divided by x raised to the x, then we can take the natural log of both sides of this and get then that the natural log of y is equal to, push the limit inside, the limit as x approaches infinity of the natural log of 1 plus 1 divided by x raised to the x. Now we can take this x and move it into the front using natural log properties, and we get that the natural log of some value y is equal to the limit as x approaches infinity of x times the natural log of 1 plus 1 divided by x. If we attempt to evaluate this by direct substitution, and we evaluate these 2 parts independently by direct substitution, right, we get, well, as x approaches infinity, x is infinity, infinity times, and this in here turns into 1. The natural log of 1 is 0. We get infinity times 0, which is what we had a moment ago. So then we have to think of this as an f and a g and decide, do we want f over 1 over g, or do we want g over 1 over f? Well, I absolutely don't want 1 over g because I don't want 1 over the natural log of that hot mess. So I'm then going to rewrite this as the natural log of some value y is equal to the limit as x approaches infinity of the natural log of 1 plus 1 over x over 1 over x. And now I've got my 0 over 0 that I'm looking for. So now I can apply L'Hopital's rule. So the natural log of y by L'Hopital's rule is going to be equal to the limit as x approaches infinity of, oh geez, I have to take a derivative of the numerator and a derivative of the denominator. Well, I'll do the denominator first because it's easier. Now I'll take the derivative of the numerator. Let's see, the derivative of that numerator is going to be 1 divided by 1 plus 1 over x times the derivative, just the inside for chain rule, so a negative 1 over x squared. Ooh, but looky, that's the same as that. So then by algebra, the natural log of some value y is going to be equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And now I'll attempt to evaluate that limit. I know that 1 plus 1 over x, I know that this denominator as x approaches infinity ends up being equal to 1, so I get 1 over 1, and 1 over 1 is 1. Now here's where people make mistakes because they think, oh, the answer is 1. No, the answer isn't 1. The natural log of the answer is 1. So then we have to say that y is equal to e to the 1, or y is equal to e. But what was y? Well, way back up here in the purple, we said y was the value of the limit. So then the final is to say that the limit as x approaches infinity of 1 plus 1 over x raised to the x is e. How's that for a terrible one? Right? This right here is about as ugly as they could possibly get. It really is. It's a horrible problem. And if you're looking at this going, was I supposed to know to do that? No, you were not supposed to know to do that. You were supposed to go, I don't know what to do. Now, if you're looking for a key that could tell you that maybe I should do something like this, it would be right here. If you have a variable in an exponent position and you don't want it there, can't have it there, can't deal with it being there, logarithms are the way that we get rid of those. We use logarithms to take derivatives. When we did that section on implicit differentiation and logarithmic differentiation, to make that happen. Okay. So, using that as our argument, what do you think we should do here? Well, before we do anything, we're going to do direct substitution and see what happens. When we do direct substitution, we get the sine of 0 to the 0. The sine of 0 is, what is the sine of 0? Well, the sine of 0 is 0, so we have 0 raised to the 0 power. Is 0 to the 0 power one of the ones that we should be looking at? And it is. 0 to the 0 power should be something that we can rewrite using L'Hopital's rule. Well, last time I had an x in an exponent position. I used logarithms, so I'm going to try it again. I'm going to say y equals the limit as x approaches 0 from the right of the sine of x raised to the x. Then I'm going to take the logarithm of both sides, and I'm going to push the logarithm inside the limit. And then I'm going to use logarithm properties to take that exponent and to move it down in front. And now I'm going to check by direct substitution what's going on here. Direct substitution, I've got 0 times the natural log of, and what is the sine of 0? 0. Well, natural log of 0, or approaching 0 effectively, is negative infinity. So I have 0 times negative infinity. So this is an f and a g problem again. And I have to say, do I want f over 1 over g, or do I want g over 1 over f? Well, I don't want 1 over natural log of sine. So I'm going to rewrite this and say then that the natural log of y is the limit as x approaches 0 from the right of the natural log of the sine of x divided by 1 over x. Right? I went with g over 1 over f rather than f over 1 over g. And so now I should have infinity over infinity, negative infinity over positive infinity, but you get what I'm talking about. Right? So now using L'Hopital's rule, so I'll put the LH in, the natural log of y is going to be equal to the limit as x approaches 0 from the right of 1 over sine x times cosine x divided by negative 1 over x squared. Okay. Algebra. Maybe it'll clear up and look like something. Cosine over sine divided by a fraction. Cosine over sine divided by a fraction. Dividing by a fraction means flip and multiply. So let's see what happens if we do that. Let's see, this is cosine over sine times x squared over negative 1. Cosine over sine times x squared over 1. If I attempt to do direct substitution, so by direct substitution, I get cosine of 0. Cosine of 0 is 1 times 0 squared over 0 times negative 1. So I get 0 divided by 0. Now what do I do if I have 0 divided by 0? Oh, 0 divided by 0. Use L'Hopital's again. So I have the limit as x approaches 0 from the right of, my numerator is cosine x times x squared. My denominator is sine x, and now my denominator is going to become negative cosine x. Sine is cosine, negative 1 just tags along. My numerator, I got to take the derivative of that mess. So let's see what's going to happen here. Let's see, cosine times x squared, that's product rule. So that's going to be sine x times x squared plus cosine x times 2x. And now we'll do direct substitution. Direct substitution is going to give me sine of 0. Sine of 0 is 0 times 0 squared plus cosine of 0 is 1 times 0 divided by negative 1, which looks like a big fat 0 over 1 or 0. So that means that the natural log of y is equal to 0. But if the natural log of y is equal to 0, then y is equal to e to the 0, and e to the 0 is 1. And so if I chase that all the way back up to the top, this hot mess should be equal to 1 as x approaches 0. Now, I'm not feeling comfortable at all about this. So what do I do when I'm uncomfortable with an answer? Well, I seek a different way to arrive at it. Let's look at the graph of this thing. So here I have sine of x raised to the x. Let me make this a little bit thicker so we can see it. And indeed, it does appear that as we're approaching 1 from the right, as we're approaching 0 from the right, the value of that function is approaching 1. So while this graph doesn't prove that I'm correct, it makes me feel a lot better about my answer. Right? Now, those two problems right there were really hard problems, not the hardest I've ever seen in terms of L'Hopital, but they're hard problems. Right? We have a few more to do. Actually, no, that was it. We're all done with L'Hopital. 24 minutes, not too bad. All right, have a good one.